The term operational amplifier was introduced in 1947 by John Regazzini and his colleagues in their work on analog computers for the National Defense Research Council after World War II. The first op-amps used vacuum tubes rather than transistors. Operational amplifiers are among the most widely used building blocks in electronic circuits. An op-amp behaves like a voltage-controlled voltage source. It can also be used in making a voltage or current-controlled current source. An op-amp is an active circuit element designed to perform mathematical operations of addition, subtraction, multiplication, division, differentiation, and integration. The ability to perform these operations is the reason it is called an operational amplifier. It consists of complex arrangement of resistors, transistors, capacitors, and diodes. Op-amps are commercially available in integrated circuit packages in several forms. A typical op-amp is the 8-pin dual inline package or DIP. An ideal op-amp is an amplifier with infinite open-loop gain, infinite output resistance, and zero input resistance. Due to infinite input resistance, currents into both input terminals are zero. The voltage input across the terminals is equal to zero. These two characteristics can be exploited by noting that the input port behaves as a short circuit, while for current calculation, the input port behaves as an open circuit. An inverting amplifier reverses the polarity of the input signal while amplifying it. The non-inverting input is grounded. Vi is connected to the inverting input through R1 and the feedback resistor Rf is connected between the inverting input and output. The voltage gain AV is equal to V0 upon Vi is equal to minus Rf upon R1. The gain is the feedback resistance divided by the input resistance. This means that the gain depends only on the external elements connected to the op-amp. A non-inverting amplifier is an op-amp circuit designed to provide a positive voltage gain. The input voltage Vi is applied directly at the non-inverting input terminal and the resistor R1 is connected between the ground and inverting terminal. The voltage gain AV is equal to V0 upon Vi is equal to 1 plus Rf upon R1. Again, we notice that the gain depends only on the external resistors connected to the op-amp. Instrumentation amplifiers. One of the most useful and versatile op-amp circuits for precision measurement and process control is the instrumentation amplifier or the IA, so called because of its widespread use in measurement systems. Typical applications of IAs include isolation amplifiers, thermocouple amplifiers, and data acquisition systems. An instrumentation amplifier typically consists of 3 op-amps and 7 resistors as shown in the figure. This circuit is represented in the form of a schematic symbol shown here. For convenience, the resistors are made equal except for the external gain setting resistance Rg connected between gain set terminals. Here, the voltage gain becomes 1 plus 2R by Rg. As we can see from the figure, the instrumentation amplifier amplifies small differential signal voltages superimposed on larger common mode voltages. Since the common mode voltages are equal, they cancel each other. The 3 major characteristics of IA are: the voltage gain is adjusted by one external resistor Rg. The input impedance of both inputs is very high and does not vary as the gain is adjusted. The output V0 depends on the difference between the two inputs V1 and V2, not on the voltage common to them, that is the common mode voltage.